Okay, so thank you. Hello everyone. My name is Valentina Macchiarulo and I'm a PhD student from the University of Bath. So I will start with a bit of background. So, it's not working. Okay. So, modern cities constantly deal with problems like the lack of surface space, the traffic congestion, and the growing level of pollution. And the mostly adopted solution is the realization of large underground transportation systems. So, this is something that is taking place in every part of the world. Just to give you some examples, I summarize some of the biggest underground projects. I don't know why it doesn't work. What's the problem? Okay, so maybe I should, okay, thank you very much. So, okay, and so all these scenarios are quite different, but they have something common, and so all of them involve the excavation of tunnels. They're really expensive. And of course, the construction industries are always concerned for the risk of subsidence after the excavation. And the settlement is something that we should worry about, especially if the excavation takes place in an area with an existing building environment. So, even applying modern tunneling techniques, it's impossible to avoid the generation of some settlement. And the associated ground movements typically propagate up to the surface, with the implication that the buildings located on the ground above the tunnel track can be damaged or experience some cracks. And of course, this is something that we'd like to avoid, especially if we're talking about historical buildings. So, in order to protect our buildings, we needed some monitoring, and the traditional monitoring is based on is implemented by means of ground-based installations that involve the use of instruments that need to be manually installed on the surfaces that we want to monitor. And as you can see from this picture, in order to effectively monitor one building, we need a big amount of sensors. But these sensors are really expensive, and the main choice in this kind of construction projects is that usually we only install sensors on few tens of buildings, while the number of buildings that can be potentially affected by the tunneling are typically ranged between some hundreds to few thousands. So, this is a problem, especially because the measurements that we collect during the monitoring phase should be used as an input in damage assessment procedures. And this should allow us to make a prediction about the building level of damage into structures. But, so the main goal of the first stage of the assessment is try to make a preliminary identification of buildings in a risk condition. And so in order to do that, we need to quantify the ground movements. The problem is that the building, we know that the building on the soil in some way as an effect on the settlement profile, but because of the shortage of building measurements, since, as I said so far, we cannot install the sensor on the structures, we cannot quantify the actual settlement for the buildings. So, the first stage of the assessment is typically performed by adopting the greenfield assumption, in which we basically calculate the settlement profile and condition in which there are not any building on the soil surface. And the problem is that this estimation typically brings to conservative results, and okay, we like to be safe, but being conservative in a kind of project in which the number of buildings involved is so high, in some way makes has a significant impact on the final project cost. And so we would like to do better, we would like to be more precise, and in order to do that, we try to look for an alternative monitoring tool. So, promising solution to this problem is given by modern InSAR techniques, and a typical InSAR system consists of satellite-based radar that basically emits a signal in the form of an electromagnetic wave, the microwave band, and this signal will hit point target located on the ground surface. The point target can be everything, like a building in our case, and the point target reflects the signal back to the satellite, and by exploiting the time delay between the emitted signal and the backscattering one, we can measure the vertical building displacement. So, this technique seems to be really good for our application, and especially because it's able to provide high-resolution measurements, and this technology can operate with every weather condition, even during the nighttime. And again, the other good thing is that because of the global coverage of the satellites, we're able to basically to monitor large areas all over the world at relative zero cost. And in the end, the amount of measurements that we're able to collect in this way is much larger than the ones that we would be able to obtain with the traditional monitoring. So, there are many versions of InSAR techniques. The one in which we are interested on is named Multi-Temporal InSAR, and basically this technique exploits the high frequency in orbit repeats to collect many acquisitions in a certain time lapse. So a typical SAR acquisition looks like an image on a grayscale. With this technique, we can collect a pile of SAR of images, and after the processing of these images, we can retrieve a cumulative displacement map. That is basically a map giving us the distribution of the building displacements over the monitor area. And the good thing related to this technique is that we can reach an accuracy up to the millimeter scale. So, but now the question is, how can we integrate the InSAR-based monitoring tool with damage assessment procedures? So in order to do that, we have developed a semi-automatic tool that is using as an input the InSAR-based measurements to retrieve, to make a prediction about the level of damage into buildings. So the tool, the algorithm, is basically can be divided into main parts. The first part of the tool performs the analysis in the traditional way. So we use the tunnel geometry to retrieve the greenfield settlement. And so the first part of the method, the settlement profile, is retrieved in a completely analytical way. And we combine the greenfield-based settlement with the building geometry to calculate critical strains to structures. The second part of the method, the InSAR-based measurements, are used to retrieve a more reliable settlement profile. So basically, since we have basically measured the building vertical displacement, the settlement that now we retrieve is based on direct measurement. And again, we combine this information with the building geometry to recalculate critical strains. The tool is also able to automatically interface with GIS system, and the results are visualized in terms of damage maps. So, just to give you an idea of the set of InSAR data that we used, this is a cumulative displacement map, and this has been obtained after the processing of 72 SAR images acquired between the 2011-2015 by the Cosmos Climate constellation of satellites, and you can mainly notice two things. So the first thing is that you can see the density of the measuring points that we have with this kind of technology, and the second thing is that you can recognize the tunnel track that is emphasized by the red scatters in the center of the picture, meaning that the settlement occurred in that area. So, before I've quickly mentioned the fact that we are able to retrieve the actual settlement profile for each building. So this is the analysis that we do for every specific building. So the first part, we retrieve the light blue curve, that is the greenfield profile, that is basically a Gaussian shape. And for each building, we identify the building measuring points that are the black dots there. And by interpolating these points with a modified Gaussian function, we retrieve the black curve that is the actual settlement profile for that structure. And the difference between the black curve and the light blue curve quantify the soil structure interaction effect. So the developed tool has been applied to a test area in the central London. And so this is an area of 25 square kilometers. And this area is crossed by the Crossrail twin tunnels. And these are the buildings in the monitoring area. So this is a really interesting case of study because there are different typologies of buildings. So we have traditional masonry buildings, we have concrete frame structures, we have buildings relying on piles, ground-bearing foundation. And so the amount of measurements that we have combined with the variety of buildings allow us to perform interesting analysis between the building's behavior in the settlement condition and the structural and foundation typologies. And we are currently working on that. So let's go to what we obtained. So the tool has been successful on 460 buildings. And what we found is that the buildings in the monitored area have experienced a negligible risk of damage. And in order to relate the critical strain that we have calculated with which level of damage, I've defined 3 categories of damage on the basis of the range of strains that we found. And the letter A corresponds to the lowest category of damage, the letter C to the highest, of course, in the range of strain obtained in relation of the highest range of strain that we found. So now I compare the results obtained with the 2 parts of the method. And what you can see, I summarize the results in terms of pie charts. So what you can see is that in the greenfield-based prediction, the 20% more of buildings experienced the highest level of damage, confirming that the greenfield-based approach overestimates the final prediction. So now I can draw the following conclusions. So the approach that I've described so far allow a quasi-real time and more reliable assessment over hundreds of buildings. And so this technology, the amount of measurements that we have thanks to the InSAR-based technology combined with can be effectively used to improve damage assessment procedures. And the fact that we have a large amount of measurement that contain information on the structural interaction allows us to investigate, understand better this phenomenon. And so the continues to work in this direction. There are promising possibilities to complement the ground-based monitoring in the future. Thank you.